Before we get going, here's a intro to probability concepts from Professor Steiner of the University of Michigan.
You have an important step tonight as you and X Division champion Petey Williams take on the unlikely duo of Kurt Angle and Samoa Joe.
You know, they say all men are created equal, but you look at me and you look at Samoa Joe, and you can see that statement is not true. See, normally if you go one-on-one with another wrestler, you got a 50-50 chance of winning. But I'm a genetic freak, and I'm not normal. So you got a 25% at best at beating me. And then you add Kurt Angle to the mix, your chances of winning drastically go down. See, the three-way at sacrifice, you got a 33 1/3 chance of winning. But I got a 66 2/3 chance of winning because Kurt Angle knows he can't beat me, and he's not even going to try. So, Samoa Joe, you take your 33 1/3 chance minus my 25% chance, and you got an 8 1/3 chance of winning at sacrifice. But then you take my 75% chance of winning, if we used to go one-on-one, and then add 66 2/3%, I got 141 2/3 chance of winning at sacrifice. See, Joe, the numbers don't lie.
We're going to get going with probability, and I just wanted to go over probability concepts with you. So these are the concepts that you've got to understand before you can do the rest of probability. So probability, let me grab a pen, is the likelihood of something happening. I don't think I've spelled that right. I don't think there's an E. Of something happening. Okay, but we do it in a formal sense. So the shorthand is P and then brackets an event equals some number. So if I put that number there as 0.5, what that would mean if you're reading it back is you would say the probability that this event happens is equal to 0.5. So it might happen, it might not happen. You can write it as a proper fraction. You can write it as a percentage if you wanted to. But what it means is that the event that's described here has about a 50-50 chance of happening or not happening. So the classic event would be, of course, probability of getting tails in a fair coin toss is 0.5, which is 50, if we want to put it that way, 50%, and so on. Okay, that's basically what that little bit of shorthand here means. I'll just highlight it so you can see that that is the formula that we're going to be coming to again and again. Well, not really that formula, but that format. Experimental and theoretical probability. So let's say I had a magic bag, and in that magic bag I had different coloured marbles. So I had two blue marbles, two kind of orange marbles, a green marble, and that kind of magenta pink. Okay, what's the probability of putting my hand in there, closing my eyes, putting my hand in, and choosing a blue marble? Well, the way we would do it is it's the number of things that we're looking for divided by possible number of outcomes. Fair enough. So how many blues are there in this magic jar? 1, 2. There's 2 of them. How many marbles in total are there? Well, 1, 2, 3, 4, 5, 6. So it's a 2 and 6, which we can simplify as 1 and 3. That would be theoretical probability. Experimental probability, though, would be that if we repeated this test thousands and thousands and thousands of times, and for some reason we found that we only got blue 1/10 of the time, that would be the experimental probability, and in this case it would probably mean that there is something wrong. So it's the probability that comes from an experiment, and then if we repeat the experiment, get the same probabilities, that's experimental probability. But theoretical probability that we're primarily really interested in is what are the number of things we're looking for divided by the total number of possible outcomes. And it works with the coin toss. So a coin only has 2 sides, or a normal coin, a head and a tail. There are 2 outcomes, often called the outcome set. So it's a set of 2 possible outcomes. We can only choose one of them. They're both equally likely, so it's 1 outcome out of 2 possibilities. So therefore the probability of heads equals the probability of getting tails equals 0.5, or equals half. When I was living in Melbourne, I lived next door to the casino in Melbourne, and I didn't really gamble at all, but they had some really, really good sports bars in there, so we used to go in there and watch the sports. But what I noticed there were a lot of people sort of hanging around the roulette wheel who weren't necessarily gambling, but were sort of taking a note and a running tally of all of the outputs, all of the ways that the ball was dropping. And if you're not familiar with what one of these things looks like, I'm going to put a little video on top of this video. So the thing they were looking for was that they were counting for, say, the number 17 came up a lot. Okay. They would go and they put all of their money on 17. And they would invariably lose money. Why? What is the fundamental rule of, or law of probability that they're ignoring? The thing that they're ignoring is the difference between independent probability and conditional probability. What they didn't seem to realize was that every event was independent of the last. Okay, so the probabilities did not change. The probabilities did not change. Okay, so the table and the roulette ball are not talking to each other. They're saying, well, 17's come up quite a lot. Oh yeah, we'll give someone else a go. Or tonight, 17's night. They don't change. In fact, if 17 kept on coming over and over and over and over again, the people who'd be taking notice would be the casino itself, because it would mean that something would be wrong with their table. These events are the events on a roulette wheel are independent. They thought that they were conditional. They thought that past events can change future and current events. Okay, so if independent means the probabilities do not change because of previous events. Do not change because of previous events. Conditional means that they do change given some other event. Okay, so a gambler's fallacy, the people who would write down the numbers and then bet according to where they think the trends are going, they thought that the probabilities were conditional when they were in fact independent. Independent meaning the probabilities do not change, they just have the same probability every trial. For our purposes, mutually exclusive events are two events that can happen but just cannot happen at the same time. One kind of cancels out the other one. So if we go to our magic marble container, the event choosing an orange marble and choosing a green marble, both of those events are possible, but they're not possible if I say choose one marble and one marble only. Okay, you can't choose an orange and a green marble, because you can only choose one. It can be either orange, or it can be green, or it could be one of the other marbles, but you can't choose them both at the same time. They are mutually exclusive. Okay, so say you have a test and you can either pass or fail the test, right? You can't pass and fail. It's either or. You could say, okay, I got 50%. That would still be a fail in most classes. Okay, so east is east and west is west, and never the twain shall meet. Simple and compound events. So simple and compound events are events similar to this one. So this is a simple event. I flip a coin and I get heads. Flip it again I get tails. Flip again, I get tails again. So you can see this is a simple independent event. Independent meaning the number of times, the probability of getting tails is exactly the same as getting tails before. Now what I'm going to do, now what's the probability of rolling a 6 and flipping heads? So now it's a compound test, so heads and flipping 6. So I'm going to flip and then I'm going to roll the dice and I get a tails and 4. So in this case it fails. So let's say I want to get heads and 2 on the dice. No. Okay, that would be a compound event because it relies on 2 things combining their probability.